Alright, I think we're live. Okay, so we are solving this problem from CSES problem set today, and it is called the number spiral problem. So do check out the problem. I have given the link in the description. So let's solve it now. Okay, so we can see that in this grid, the grid that is generated from this pattern, we are given an x or y coordinate, and we have to return the integer that is present in this grid, right? So one key observation we can derive from this subgrid as an example that has been given to us, that the values are essentially propagating in this manner. So each arrow represents the starting point of that new subgrid that is thus formed at each increment in the cell, be it row or be it column. So basically this is a starting point of uh, this layer of the grid, and this propagates forward, thus forming a larger square. That, like, the an additional layer always completes the matrix, thus that it becomes a square, right? So, and one another key observation we can derive is that in the ith column, the range can only be till the square of that column, right? So this is the observation. Like, I just write this again. So let me, yeah, so let's follow this subgrid, right? So if we see, like, these are the subsquares, like this is the next layer, this is a square thus formed, like the matrix is again complete, it's kind of a square, and then an additional layer is thus passed, and we get another bigger square, right? But for the I can remove this. For the let me point this as index. So for the index 0, 1, 2, actually let's start with one base indexing, right? So this will become 1, 2, 3, and this, right? So we can see that in this layering, this layer is this, right? So this is the layer that is formed by this number of column, and this is a consequent range, right? So this just forms a series, and this series is nothing other than like just consecutive natural numbers. But we can order this in a manner like this range will always end at 4, or in this case still the maximum value this range will have is 9, right? So for 2 we get 2 squared, and for 3 we get it squared, right? And this is formed, this range actually has a minimum value as well, and in a closed formula form we could write it as like, if the upper bound for this range for the series is I square that is included, and thus the lower range, the lower bound for this range will be I minus 1 squared, that is the maximum of the previous row that we would have encountered, and plus 1, right? uh, I Yeah. So take a moment to analyze this. Basically this is the bound that we get for the ith index column, and in a general formula, right? So in a general formula, so this is a matrix that is given, and x and y. So if this element essentially can be present at any instance of this place, right? So it could be present here, it could be present here, it could be present here. So how do we define, like, how do we decide which column it follows, which column's range it follows, right? So we are trying to define a way to essentially get a order in, like, what will be the range of this element. So we can always define I as the max of x and y, right? Like, the maximum value between these coordinates. So if it were to be 2, it is 2 2, so like again it's 2, so this range is still the correct range. But if it were to be 3 and 2, you can see that the range is actually following the, like this somehow skewed reverse L always follows a pattern, always is defined by the maximum of the indices present given to us, right? So I is always x and y, maximum of x and y, and the lower bound and upper bound are thus given to us. So for any given x and y coordinate, we can define the range that will be like we have derived a range successfully. So we are like trying to formulate a solution here, right? So what do we do now? So now we need like let's say the x and y were given as like let's take this, right? So 2 and 3 were given. So we define I as 3, and we thus get a range as I minus 1 squared, that is 2 square, so it is 4 plus 1, that is 5, that is 5, and 3 square it's 9, and these both values are included and we get a range successfully, right? So another thing, this range thus formed is actually has a special ordering to it, right? So if we try to decide to look at from the rows perspective, right? So we like try to consider this range as a continuous array and not this L-shaped thing. So what do we get? We can see that sometimes this range actually starts from I square and then ends at let me just paint it in a different color. Sometimes it start at I, sometimes it actually start at the lower bound, right? So it is reversible. And how do we decide that? We can decide that by using the parity of the column provided to us. And it is actually very useful here because the indices provided to us is actually also one based indexing, so that is good. So we can see that if the parity of the ith cell is positive, basically we are trying to see the range in which this is given to us. So we will check the parity of I only, that is the range that we are taking here, right? So here we are taking this range and we take the I value, that is 3, and we check its parity. We can easily do that by using 3 and 1, that is a bit operation, and if it returns anything, that if it returns 1, then we know its parity is actually odd, right? So it is odd and it returns actually that only right here. And we know that like we can define it as, if it is odd, then the range will always start from the lower bound and goes to upper bound. So I can define parity here if parity is 1, otherwise if parity is 0, right? So in case of parity reverse, so we reverse this range, and in Python we can easily just iterate over this array, like we can define this array, and this will thus become 5 6 7 8 and 9. So we have thus formed a valid range for the index that we have provided. So our final task would be to define which of these elements is actually the required index, right? So how do we do that? Another thing that we can observe from this grid is that the values actually go in this manner. Like I have, let's just draw it again here. So it is 5 6 7 8 9. This is actually ordered like 5 8 7 6 9 8 7 6 5. Yeah, so these values actually form a kind of curve, right? So the indexing for this, so this forms some sort of like an increasing and decreasing indexing here. So what I mean by that is here, like apart from the middle element onto the left side, these indexing are dominated by the y indexing of the coordinate given to us, and on the right side of this indexing is governed by the x coordinate. And how do I know that? Because this, the middlemost element, is actually the place where x and y are the same. So x is equals to y, right? So in in the other instance the x remains the same, right? So the x remains the same for this whole thing, it is always x, and for this thing it is always y. And we have derived this range. So we know that after the middlemost element we need to check for the x coordinate, that like the only the x coordinate will define which of these values. Like we could potentially just cut down this array in the middle if we know like what is the value that governs the indexing, right? And how do we do that? So we can do that by like checking if I is equals x, or I equals. Where does x govern this? X govern this right here, right? So if I is equal to y, the range gets divided into this subarray. While if this were to be x, if I were to be x, the subarray thus divided becomes this, right? So in this case, actually, the range is actually this only 7, 8, 9. So we come down, and how do we know what is the right answer right now? Just like know that we need to move from the end of this point, right? So we're going to do just that. We define this length of this range thus formed. Let's call it r, and we can just actually do this. We can actually just negate 1, that is will give us the indexing present right here, and we can move by x minus 1 times, right? So basically these values are governed by x coordinate, and x minus 1, basically this is done because x coordinate is given in the instances of 1 base indexing, right? So we need to deduct 1 from here, and this actually gets cancelled out, and we are left with length of r minus x, and that is actually a correct solution for this case. While in other case, so imagine if the maximum value were to be x actually. So we know that the value is defines the point where this subarray has a solution, and that is actually pretty simple because we are initially present at this, we should be present at this, that is 0. And how, by what value do we move forward, right? So we know that here only the y coordinate defines this, so we could potentially call so this is in, okay, so let me just subject this inside this range. So this range is calling the value inside of this. Yep, that's correct. And in this instance I is great. So what we do, we go we call r, and what value do we call? We call y minus 1. Again, this is because it is one base indexing, right? So this returns our y coordinate, that was the minimum coordinate among the coordinates, and we deduct it by 1, and this is the valid answer. So let's actually code it up. Let's see. First of all, I think we need to, yeah, all right. So first of all, we need to take in the number of integers there. So for I in range, we go int input, we need to take in x and y. We can easily map them inside this function called split. Yep. All right. So first of all, what do? We define our I value, right? So right here, first of all, we define our I value. So I is maximum of x and y, and next step is to generate the series. So we can easily generate it in Python. It is pretty easy right here. So what do we call? We go for a in range. We know the range. This range is basically I minus 1 squared plus 1, and it goes up till I squared plus 1 because the range upper bound is also included, and so we simply can do series dot append a, right? So we can actually see this series just for debugging right here. Number dot py. Okay, Python. Okay, so we made a problem somewhere like, okay, it's easy to fix. Alright, so we can generate a series right here. We could use 3 and 3. So one test case, and for 3 and 3 we get 5, 6, 7, 8, 9. Perfect. And what do we do next? We essentially check, like, if the series, we need to check the parity of the maximum index, right? And if it were to be even parity, we basically reverse this series, right? And in Python that is also pretty easy. We could simply call I mod 2, or I could just simply call I and 1, and if that's true, is to be reversed, right? We can go ahead and try printing the series again. This time 2 and 3, my bad. I think I should have used a different example. That is 2 and 2, and we get 4, 3, 2. That is perfect. Okay, that works perfectly fine. And the next step is basically indexing the value that we need to return, right? So how do we do that? We actually check if x is equal I. Basically we are going for this condition right here, right? So if x is equal I, basically the answer is essentially only dependent on the y coordinate, right? Dependent on the y coordinate, and we can simply do a y minus 1, and in other instance we could simply call it series, len of series minus 1 and minus x plus 1. So this is just a expression without doing the minus indexing, right? So as you can see right here, this is the output that's generated, and it actually matches our indexing on the grid. That is, the first and first element is 1. I essentially just printed, like, gave commands to print the first row, and that is 1, 2, 9, 10, and 25. That works perfectly fine. And this is actually a correct solution conceptually, but as you can see right here, when we submit the solution, we actually get a time limit exceeded error, because essentially what we are trying to do, we are generating this entire series, right? So this entire series was going to I minus 1 squared up till I squared, and for a input bound of uh, basically, I think that is 10 to power 9, right? So it is 10 to power 9. It could be 10 to power 9, right? So for 10 to power 9, this subarray thus generated is actually, like, the x and y could both be 10 to power 9, right? So what can imagine is, this is 10 to power 9, and this is also 10 to power 9. So the elements thus generated are all in all is 2 into 10 to power 9, right? This is the length of this generated series, and essentially just like doing operations on it, even in linearly, right? So we are not doing any square operations, but even linear operations actually results in a time limit exceeded, and that is perfectly valid. So we need even better uh, closed form formula that can return just the conceptually the right output, and that is actually very easy. So this whole part of what we just did just now was actually just to explain, like, we are explain the pattern that's formed by the series, right? So basically, how can we now, like, get the correct solution? So there is 3 steps to it, like 2 or 3 steps to it. First of all, declare I, then we declare our starting variable. So we could declare it start variable, or we could simply declare it result variable. This result variable will initially can be 0, it can be anything actually. So if first of all we check the parity of the series we are getting into, right? So if its parity is 1, like if its parity is 1, it is different case, and if it were to be 0, it's a different case, right? So if its parity is actually 1, so we know that for one parity, basically an odd instance of the maximum cell present. So we define the range, and we start from the b I, basically I minus 1 squared plus 1, right? So we define result again. We go for I, uh, we get the starting element of the series, that is I minus 1 squared plus 1. And for next step we check the same thing. So same thing, what same thing about if I is equal x, so basically which is governing the subarray, right? Which index is governing subarray. And if it were to be x, the result is simply, basically we are now not checking the value present in the subarray, actually we're generating it. So how can we do that? We basically plus 1, like we plus 1 for every movement in an index for one value, and we do it till the index is present, right? So that comes out to, because the step is actually just one, it is a series of natural number of, you could call it a arithmetic progression with the difference of 1. And we get this answer simply as y minus x, and it's as simple as that. So basically the index itself just reveals how much do we add to the start value. So like if it were to be index were to be 2, right? So we actually, like this is 3 in actually, so if index were to be 3, we minus 2 from it because it's one index, so it becomes 2. And if we add 5 to 2, that gives us 7, right? So we don't even need to maintain this array all in all just to get the answer, because we could just simply add the target index to the current starting element. So we use the arithmetic progression thing, and we get this result plus 1. And in the other case we do this kind of similar thing. We add 2 into I. Why do we do this? So we do this to get the most right element of this series, right? So, and as we discussed right here, the length of this series becomes 2 into 10 to power 9. And why is that? Because 10 to power 9 elements from this side and 10 to 9 elements from this cell, and we get one overlap, but that's doesn't, like that can be negligible, that is negligible. uh, so we get the most right element, and we could just subtract the index that is responsible for this thing now, right? So we always start from the bottom left value that is present in this series, and then we add and get the most right element, and then we can just subtract to the minimum, to the target element, right? And that is pretty simple also. And what is the formula for that? We do 2 into I, and then we subtract 1, and then we subtract 1 it as well. And this is actually the final answer. And and similarly for the parity 0 case, the result is actually initialized as I squared. And for if I were to be equal x, we do a similar thing, except we subtract this time, because the starting element is actually the I squared value, right? So this is actually 4. So this time we are subtracting, and we do this similarly. We do a result y minus 1, and in else case we can simply do result equals to minus 2 into I, just getting the bottom, like the bottom of the value in ordering, or the last element of the series, and we subtract x minus 1, right? So actually just let's just get rid of this. We don't even need the series now, and we simply can check if I and 1, right? So the parity is odd. So we initialize our result as I minus 1 squared plus 1, and if I is equal x, so we basically know that y is responsible for it, so we simply add the indexing of that. and in other case we get the last element of the series and get this by multiplying our index to it, right? And we need to subtract and get the target element. And in other instance of this, like if it parity were to be 0, we initialize our result as I into I, that is I squared. And if I equals x, we can simply subtract y minus 1. Else we could just yeah, so else we could 2 into I minus x minus 1. Lastly, we print our result finally, and I think this is it. Let's just try this. All right, 5 comma 1 1 comma, oh, all right, 1 comma 2 comma 3 1 comma 4, right? So this is another value that is apparently present in the grid because our solution is, our logic is sound. I think this should work. We could submit it right now. As you can see, it's accepted, and this is the final solution. Thanks for watching.